Today I'm going to be also talking about fast radio bursts. In particular, we're going to be looking for gravitationally lensed FRBs using CHIME FRB, which also saw the big SGR 1935 burst that Nayab described just now. As we know, fast radio bursts are bright millisecond duration radio transients originating at cosmological distances. Their origin since their first discovery in 2007 remains a mystery. However, now from the, thanks to STARE-2 and CHIME, we now have strong evidence that suggests that some of these bursts are associated with magnetars as their central engines. The situation we're interested in today is in the gravitational lensing of these transients. So in this picture, there's an FRB acting as a backlight, and light from the FRB gets bent by the foreground spacetime due to some foreground lensing mass. And we see multiple images of that burst on Earth. Now, lenses come in many different shapes and sizes. And in this cartoon, they're shown as a galaxy scale lens. But the whole reason why we're interested in FRB lensing is so that we can use observations of this multipath propagation in order to detect black hole dark matter. That multipath propagation that I just described has a couple of different experimental signatures, and the phenomenology is very rich. So as you can see in the simulation or this animation produced by Scott Gowdy, there's a lot of things going on here. First, there's the lens shown in yellow, stationary at the center. And then there's a transiting backlight moving behind that lens. And you can see that it produces multiple images shown in blue. Those images themselves change in shape during the transit. And also the brightness of the images changes over time, as seen in the rise and fall of the microlensing light curve on the bottom. There's another experimental signature of gravitational lensing, which is that if you were able to resolve this in the time domain, you would see one of those images arrive at a different time than the other. And that's because along these two different lines of sight, there's a different gravitational potential, and therefore you're measuring a differential Shapiro delay between the two images. Each of these observational signatures has been seen in the universe in the strong gravitational lensing of quasars, to the distortion of the anisotropies of the cosmic microwave background, to the direct observation of microlensing light curves towards the large and small Magellanic clouds. But this fourth experimental signature has received very little attention until lately. And that's what we're going to be talking about in this work. We're going to be using time domain information, just time domain information, to search for gravitationally lensed FRBs. So at this point, you must be wondering, why can't I do this with my favorite transient? All you need is something that changes in time. And the short answer is absolutely yes. You can use your favorite transient to do this. There's a paper in Nature Astronomy by a group at Monash, which presents evidence for an intermediate mass black hole exposed by a time domain search for gravitationally lensed GRBs. However, the long answer is that there are some reasons which make FRBs particularly good at this kind of time domain fishing experiment. For one, FRBs are extremely common. They occur at a rate of about 10,000 over the night sky per year. FRBs are also come from compact central engines, probably from magnetars, and this gives them a very short time scale. So you can see here on this one-dimensional projection of the transient phase space plot that FRBs are already some of the fastest transient in the night sky. But there's an additional dimension of information, which I haven't shown here, which is that FRBs, in addition to gravitational waves, have phase information. And so phase information is not a common concept in astronomy, but for those who do radio astronomy and gravitational wave astronomy, our antennas are sensitive to not just the amplitude or the power of the electric field, but the phase information contained in there. And this changes our lensing search dramatically, because when you have phase information, the time resolution you have is not set by the variability timescale of your transient, but instead by the bandwidth of your detector. So if you had a 1 gigahertz bandwidth radio telescope, you're suddenly sensitive to time delays on the order of nanoseconds instead of the variability timescale of your whatever transient you care about. And this actually allows us to push our physics reach to lower and lower lens masses, enabling for a very sensitive search for black hole dark matter. Put another way, here's, I really like this picture of what we're doing compared to what the gamma ray burst group is doing. Whereas you could take two light curves from your favorite transient and correlate them to measure a time delay. Your fundamental observable there is the power or the intensity. And that gives you a time resolution limited by how fast the transient rises and falls. However, when you have phase information, what you're doing is it's equivalent to taking the electric field, propagating around the gravitational lens, and taking that electric field and interfering it at a beam splitter and measuring the fringes of the output. And that gives you a much greater time resolution and turns out much better sensitivity than the incoherent search method. And that's what we're trying to do with the fast radio burst that you can't do in other parts of the electromagnetic spectrum. How are we finding fast radio bursts? To begin with, we used the world's best fast radio burst finding machine, the Canadian High Intensity Mapping Experiment. This is a phased array beamforming interferometer operating over a wavelength range corresponding to 400 to 800 megahertz. The telescope bandwidth, therefore, is 400 megahertz, giving us a time resolution of 2.5 nanoseconds. We buffer data at an enormous rate, and when we detect an FRB, our real-time search pipeline says, stop, save that data, and we can process that data later offline. What makes CHIME so great for discovering FRBs is its enormous field of view. Here you can see the whole northern sky turning underneath CHIME's beam, which is shown in red. This field of view spans hundreds of square degrees across the sky, and this enables for transformative FRB science. So whereas between 2007 and 2018, there were only about 50 FRBs discovered serendipitously in surveys, a year of CHIME surveying yielded 700 FRBs sampled with a uniform selection function, which has the potential to dramatically change the landscape of FRB science. And it is this data set that we are starting to carefully look through for lenses. So we have the voltage data for an FRB. All you do is you autocorrelate that. And here I've shown that autocorrelation function as a function of delay. So you can see that this autocorrelation function has a lot of rich structure. The x-axis is measured in nanoseconds, and the spectrum goes out all the way to the duration of the data that we save, which is about 100 milliseconds. And the presence of black hole dark matter or other lenses along the line of sight would show up as either positive or negative peaks in this space. So you must be thinking to yourself, oh, well, there are clearly a lot of peaks here, so you must have already found something. However, the story is a lot more complicated than that, because it turns out that reflections in the telescope at short delay scales and radio frequency interference on long delay scales actually contribute significantly to the foregrounds. So we have to veto all these events before we can say that we've conducted a search with due diligence. And so a better answer to the question of what we saw is, what do we actually expect to see? So what do we forecast? How sensitive is lensing measurement? And the way you can make that forecast is as follows. For every FRB that you measure, that transient comes from some magnetar in a galaxy far, far away. So you'll draw a pencil beam out to that galaxy, and that pencil beam has an annular profile. The inner edge of the annulus has a limit given by the time resolution of your search, and the outer edge of that annulus has a size limited by the burst brightness. So if you see a brighter source, then you can probe a larger pencil beam along the line of sight. And if you push time resolution like we're doing, this annulus closes up into a circle. And within that volume, with basic cosmological assumptions, you can predict the number of lenses that you actually expect to see. And you can do this for every single burst sight line and stack over burst sight lines to probe many, many different pencil beams at different directions throughout the universe towards each of the FRBs that you see. So here is the expected number of gravitational lenses that we expect to see in our search as a function of the lens mass. So the way to read this is you look at the black curve, and if all the dark matter were made of point masses within a decade, say between 1 and 10 solar masses, we would have a 55% chance of seeing one of those along just this one burst sight line. So it's an extremely sensitive search method. You can see in the different colors of the plot that the short delay scales are what gives us sensitivity to lower mass lenses, and the longer delay scales are what gives sensitivity to the larger lenses out in the universe. And so with hundreds of bursts, using this technique, we will either rule out black hole dark matter over a wide range of masses or detect it. And so in conclusion with this, we have developed a powerful phase coherent time delay search method that can detect MACHO dark matter candidates, for example, LIGO mass primordial black holes, or rule them out entirely. And we have a large sample of events to be processed. And none of this work would have been possible without the help of my collaborators, Zarif Kader, who is a master's student at McGill, Prof. Matt Dobbs, and my advisor, Kiyo Masui at MIT. With that, I would like to thank my collaborators and the rest of the CHIME collaboration for making such a phenomenal experiment possible. And now I'll take any questions.